Well, thank you. Another talk about session types. This is with my co-authors, Atsushi Igarashi, Vasco Vasconcelos, and Phil Wadler. And I have to admit that I just removed one slide of introduction to session types. I hope you appreciate. Instead, I'll tell you that I happen to be the manager of this company, and I have two super capable programmers. And one of them, called Sydney, he is I didn't want to say he, I'm sorry. So Sydney is a very strong advocate of static typing. And to make Sydney happy, we actually implemented a language with full support for session types and static typing. The other super capable programmer that I have around is Robin. Now Robin, and the language is called GV for undisclosed reasons. The other super capable programmer is Robin. So he's programming UniGV, unityped GV, and he's the dynamically typed guy, right? So, Robin's given a dynamically typed language with communication primitives that sort of look like session type communication primitives, but all untyped. And of course, I have a challenge for these guys. So they have to work together, right? And they have to implement a client-server architecture for me. So of course, Sydney doesn't want to give up on safety, and Robin doesn't want to give up on the flexibility that he has because of the dynamic language. All right, so doctor's advice, well, our advice. I think we are all doctors, right? Yeah, I mean the authors of this paper. Right, so our advice is use gradual session types. And at the interfaces, we prescribe that you put typecasts so that on the static side, type checking does the job and statically assures Sydney that everything's fine. And on the dynamic side, we are going to use runtime checking, which also assures that assures Sydney that everything is fine. And Robin is happy because Robin can implement things in the dynamically typed language. Now, the task. What's the task? Well, the task is to implement a service that is given by this fancy session type. I will walk very quickly through it, but you've seen it a number of times. So this is the type of a server. The server has an external choice, so you can send two different messages, neg and add. And depending on the message, you either continue with receiving a number and then sending a result and then finish. Similarly, add takes two arguments, so you receive two numbers and send a result and quit. All right. Just for completeness, I'm not sure if we've seen this before. The client has the sort of dual type where, and I've tried to highlight this on the slide, where essentially you flip all the type constructors. Yeah, so external choice becomes internal choice, sending becomes receiving, and so on. Yeah, it just flips. Right. Now, we need to choose, right? So let's say Sydney is going to task to implement the client. Yeah, so that's just the type that we saw before. And I've repeated it here on the slide. And we observe the phenomenon that you've seen in the previous talks as well. Now, so here we have a client. This client chooses to implement negation. So I'm sending the neg message, and the type of the channel endpoint proceeds through the session type. Now, so here the rest of the channel, you can only send something. Okay, the client sends its argument. Then on the rest of the channel, you can only receive the result. The client receives. Then we need to finish to close the channel. Well, actually, there's two ways of closing here. So essentially, here the client waits for the server to quit the connection. All right. So, and this is fully typed. Sydney is happy. Everything is safe and sound. Now we need to have some job for Robin as well, right? So Robin is tasked to write a server for this beast. So Robin sits down, scratches Robin's head, and the first attempt is this code. Yeah, and you see that the part for neg looks pretty similar to the code that we saw on the client side, only that send and receive is sort of flipped, right? So when negation is chosen, then we first receive something and then we send something. And when we add something, then we first receive two things and send two things. The only construct that I didn't explain is up here, the case C, that actually performs an external choice on the channel endpoint. So it checks the particular message and chooses either the left or the right code. Now, the embarrassing thing for Robin, this code type checks. But now Robin looks closely at the code and sees, oh man, look, this code for neg and for add, this looks very similar, right? There must be some way to abstract this. Ta-da! And indeed, since Robin has this unitype language, you can indeed abstract it. Yeah, so you can write this code that receives something according to n. N is the arity of the operation. You can write code that just receives an argument. It takes an operation, and thanks to partial application, accumulates the result here in this op parameter. And then finally, when there are no further arguments, it just sends the result and closes the channel in the last line. And here, up here, the first part just does the external choice and then invokes the server loop here with the two functions and the channel endpoints. Well, this is nice because, well, now we can easily extend the server with further functionality. That's why I said I'm writing here extensible code, because if I have further operations, then I can just add further lines in here. Yeah, for subtraction, whatever you want. Yeah, just another line here, and the server code down here remains totally unchanged. This looks fine, and Robin is pretty happy. And the downside is, for some reason, this is, there's more down here. Interesting. Okay. It worked 2 days ago, but I'm not sure what happened here. The projector has changed. Well, the downside is type checking fails. Right? So if we zoom down to serve op here, then we'll see, well, we can see it here at the two calls. At the two call sides, we see, okay, this argument, once it's an int-to-int function, the other time it's an int-to-int-to-int function. Right, so what's the type of op? Similarly for C, right? So that once we pass a channel endpoint that accepts where we can send one data item and receive an integer, and the other time, for add, we need an endpoint that is ready to receive two integers before it sends an answer. So clearly, we can't really assign a good type for C and for op at this point. So what do we do? Well, I already mentioned it in the beginning. Gradual typing will come to our rescue. And now I need to show you a little bit of the type structure, but only a small bit. The first line here that I'm showing you, that's what you're all familiar with from the simply typed lambda calculus. And mind you, I'm only showing you a small fraction of the typing system that's actually in the paper. And I'm trying to gloss over a lot of details here. So this is the simply typed lambda calculus with products. To make that into a gradual lambda calculus, you can look up in related work by Seek and Ta and others. You extend it with the type dynamic, which we write as star here, and that abstracts sort of any simple type, and it's unrestricted. Right. The other extension would be, this is annoying, would be to extend the simply typed lambda calculus with sessions. That would be a mini language, a subset of GV, mini GV, and it just adds another kind of types, session types, which are written here R and S. And well, you have a type to send something, and then continue with a session. You have a type to receive something, and then continue with a session, and then you have two different kinds of closing a channel. And then, and this is one of the contributions in our work, then we also, in order to gradualize this calculus, we also need to add a dynamic session type. That's this star in the circle star. And this is abstracts over any session type, and it's also a linear type. And we'll see later why that's the case. Right, and this is mediated by cast expressions, which I will write like this. And of course, we are going to run into a complication because of the linearity of the session types in a couple of minutes. All right. Right, so let's try to make our code type check again, the one that I showed you before. And I'm only going to look at the serve op part. So the first argument is actually fine. The integer is just treated as an integer in our code. The second one was the accumulating argument for the operation. So that's going to be abstracted to star. And that's just being treated as in the gradual calculi that you know. And here, this is the gradual session, the dynamic session type, which is abstracting over the different kinds of sessions. And then you get unit. OK, that's not really interesting. Now, in order to work with these two, so the C here has this dynamic session type. In order to actually do something with this dynamic session type, I need to cast it into something that receive will understand. Yeah, so receive has a type that, it requires something of this form here, receive something, and then continue with another session type. So I first need to cast the dynamic session type into this form. Similarly, but already known from previous work, if I have an operation which is abstracted to the dynamic type, I first need to cast it into star to star, into a function, so that I can apply it. All right, and then in order to call it, I need to also cast a function into int, into star, into dynamic, and I need to cast a session type into the dynamic session type. And then I can do computation. So now here I'm showing you two crucial reductions that need to take place in order to deal with these casts. The first one here is actually known from previous work, from actually since Fellais and Findler from 2002. If I have a cast that's applied to a function, then this function cast actually stays with the function until the function is applied. And only at the point where it's applied, so the W here is the argument, then we actually distribute the cast on the argument to the argument and the cast on the result to the result of the function application. And that is exactly the way that we deal with casts on the channel endpoints. So this is illustrated here with one particular communication primitive, the send operation. So if that obtains a channel that happens to be wrapped in a cast, which for technical reasons must have this form, then it's just like here in this function application case, it's unwrapped. So the cast on the transmitted value is wrapped around the argument, and the cast on the remaining session is applied to the result of the send operation. And there are similar, analogous reductions for the other communication operations. So that gets us to sending things. And then at some point, we need to get out of the dynamic type again, and out of the dynamic session type again. And that happens again analogously to previous work, for example, for the gradually typed lambda calculus. So if we have a value that is wrapped into the dynamic session type, and we want to cast it out into another session type, then this only works if the wrapped type is a subtype of the one that we're expecting. In that case, and this rule is called collapse because the two casts collapse, and in that case, we just return the value that was wrapped. The other case down here is when the type that we are trying to extract from the dynamic session type is different. Well, it's not a subtype, it's not a supertype from the one with which we wrapped it. In that case, we raise blame, and this is actually interesting because it's a new kind of blame assignment. It's a symmetric blame assignment because it doesn't just assign blame to the guy who wants to extract from the dynamic session type, but it also assigns blame to the person that actually wrapped it with negative blame. So why is that the case? Well, it turns out in the presence of linearity, we will see there is also another cast that wraps a linear type into an unrestricted type. And then the person that wraps something that is restricted into something that's unrestricted also takes part of the blame to share this thing that shouldn't have been shared. Well, and then for technical reasons, we also collect here the linear variables. All right. Another catch, or final catch for the day, is how do we deal with linearity? Suppose here we have a function that takes a channel endpoint on which you can send just one integer, and then it quits. And this here is a type-correct function that does exactly this. It takes such a channel, sends 42, and closes it. Now, if we go untyped, well, anyway, if we go untyped here, then we have an f untyped. It takes a channel, and it can try to send a number on the same channel multiple times. Even if we pass this channel here that only accepts one transmission of an integer and is then finished, and this call could pass it to this fu, in that case, we should fail here at that point at runtime. So how do we achieve that? Well, fortunately, we can invoke the fundamental theorem of software engineering, which says that all problems in computer science can be solved by another level of indirection. And that's the case here as well. Due to time, I will just go to the pictures that I can show you. So if I have a channel endpoint, that's the thing here on the left for you. If I have a channel endpoint I want to cast it to dynamic, remember the dynamic type here, the star, is unrestricted, so I can share it with whoever I like. I can duplicate it, do whatever. So in order to do that safely, I need to wrap it into a box, into a storage cell, and just pass the address. And one part of the box is also that I remember the type at which I captured the channel endpoint. Now, in order to make use of it again, I need to cast it from dynamic to a session type, as here. And what we do is this: we take the endpoint out of the box, apply the cast. So that is the type at which the box was created. R is the type at which we're going to use the session endpoint. And to remember that this channel is now in use, we override the box and lock it. Now, if somebody else comes along and tries to access the same box, like here, and tries to cast it from dynamic to some other type, it's going to raise blame. And it's going to raise blame saying that you've violated linearity. And then, in that case, you get blamed for both parties. OK. There's one more problem, but in the interest of time, I will skip over that, and I have to point you to the paper to look at that. Let me just mention the technical contributions of the paper. First of all, we elaborated this gradual type structure. We proved the usual type preservation. We wanted to prove progress, but unfortunately, we needed to water that down to something we call absence of runtime errors. But we were able to extend the results from previous work on blame safety and also the tangram theorem of Findler and Wadler to this calculus. This involves having 4 different subtyping relations, and also for the type structure, you have another subtyping relation, and in order to make this gradual, this is yet another subtyping relation. So if you enjoy having many subtyping relations in a paper, well, I have a recommendation for you. Well, anyway, okay, let me conclude. Gradual session types essentially combine the session type language, the functional session type language from Gay and Vasconcelos, with work from Wadler and Findler from the blame calculus. And this enforcement of linearity has been pioneered actually by Toff and Pucella. then you might wonder, one thing that's often used in context of gradual typing is the criteria for gradual typing. We fulfill most of them. So one is embedded of typed code. That's sort of trivial to fulfill. The other one is embedding of untyped code. That was the part that I skipped, but see the paper. And then another one, the last one is the gradual guarantee. And the gradual guarantee is best proved with a surface calculus. And right now we have a sort of a blame calculus that directly deals with casts. So right now we are not in a position to state it in an easy way, but that's going to be future work. And thank you for your attention.